Hello and welcome. My name is Lloyd Thomas Miller, and today I want to share a new way of thinking about one of the strangest features in modern cosmology, the cosmic microwave background cold spot. This isn't just about a curious anomaly in the sky. This is about the origin of the universe, the structure of memory, and a new model that may explain why we are where we are right now. That model is called the Millar Cosmological Model, or MCM. Section 1, the cold spot, what we know. Let's begin with what science already agrees on. In the standard model of cosmology, the CMB, or cosmic microwave background, is the afterglow of the Big Bang. It's the oldest light we can see, dating back nearly 13.8 billion years. This light comes to us as a uniform, nearly perfect field of microwave radiation. But there's a blemish, a region in the southern hemisphere of the sky, about 5 to 10 degrees wide, that's roughly 70 microkelvin colder than the average CMB temperature. This is what's known as the CMB Cold Spot. It was first spotted by WMAP and later confirmed by the Planck satellite. In the standard model, explanations have included a possible supervoid in the line of sight, or that it's simply a statistical fluke, a rare chance deviation in the primordial fluctuations. But neither explanation has fully satisfied cosmologists. Section 2, the MCM interpretation, the Chrissy Core and the Shatter. The Millar Cosmological Model offers something radically different. Instead of viewing the cold spot as a statistical outlier, MCM sees it as a scar, a directional imprint left behind by the Chrissy Core. In standard cosmology, the Big Bang is a singular event from which time and space emerged. In MCM, that singularity has a name, the Chrissy Core, a point of absolute stillness, absolute zero, and no dimension. This isn't just a metaphor, it's the ground state of all potential, the quantum still point before the birth of the universe. And then it ruptured. That rupture is called the shatter. This is the event that released space, time, and matter into existence. Unlike the smooth isotropic inflation of the standard model, the shatter in MCM is directional, had bias, and from that bias came a backside imprint, a rupture scar still visible in the CMB as the cold spot. Section 3, time and memory. Now let's talk about time. In standard physics, time is a dimension, part of the four-dimensional spacetime fabric described by Einstein's general relativity. In MCM, time is something more tangible. Time isn't flowing, it's being written, tick by tick, through the appearance and disappearance of quantum tension structures called arnis. Each arni connects two realms, a tessy, which is the matter side we observe, and a stuck point, anchored in a hidden antimatter realm beyond our observable universe. As these structures blip in and out of existence, they leave behind space, and each disappearance writes a tick onto the memory fabric, a foundational concept in MCM that carries the imprint of every event that has ever happened. In other words, time equals memory, and the cold spot is not just colder, it is older in memory, a deeper imprint than its surroundings. Section 4, comparison with standard cosmology. Let's pause here and compare language. In standard cosmology, the CMB is the oldest light. The cold spot is a temperature anomaly. Inflation is smooth, and anisotropies are random. In MCM, the CMB is the outer face of the memory fabric. The cold spot is the directional scar of the shatter. Inflation didn't smooth everything. It burst directionally, leaving structural asymmetries. What the standard model sees as statistical fluctuation, MCM sees as intentional geometry, the lingering signature of a structured beginning. Section 5, observational evidence in MCM's testable predictions. So what do we see and how does MCM interpret it? Phenomenon observed, MCM interpretation, supports deep not a local structure. Mixed evidence, cold spot in CMB Planck, directional scar of the Chrissy Core rupture. No corresponding void, supports deep origin, not a local structure. Lensing anomalies, mixed evidence. Memory tension distorts light paths. E-mode and B-mode polarization. These are subtle directional patterns in the polarization of the cosmic microwave background. In the standard model, they're explained as a result of photon scattering during recombination and gravitational wave imprints from inflation. But in the Millar Cosmological Model, these patterns take on new meaning. You see, in MCM, the memory fabric is not a passive backdrop. It's an active record, constantly being written by the appearance and disappearance of ARNIs. Near the cold spot, where the rupture of the Chrissy Core occurred, the fabric is more heavily folded, more deeply scarred. That fold, a permanent ripple in the quantum tension field, would cause distortions in polarization, not random ones, but directional ones. E-mode patterns would align in a biased, memory-directed orientation, and B-mode swirls might reveal torsional tension, subtle corkscrew-like effects from the angular momentum of the rupture itself. This gives the MCM predictive power. If future CMB missions like CMB-S4 detect unusual polarization alignments, especially those not predicted by inflation, that supports MCM. And remember, the standard model does not expect unique or location-specific B-mode distortions tied to a singular CMB feature. It expects it near the cold spot and nowhere else. So, how can we put the Millar Cosmological Model to the test? If this theory is correct, if the cold spot is truly the backside imprint of the Chrissy Core rupture, then there are specific, observable consequences we should expect. First, we look to 21-centimeter hydrogen tomography. In MCM, space is created with each ARNI event. So near the cold spot, where the rupture seeded structure directly, we expect a slight anisotropy in hydrogen distribution. It's subtle, but over cosmic time, these anisotropies could be preserved in the large-scale structure. Deep hydrogen mapping might reveal faint directional fingerprints in the form of density gradients or clustering asymmetries in the neutral hydrogen fields around the cold spot. Second, we look at CMB polarization surveys, especially those from future missions like CMB-S4. As we just discussed, the memory fabric in that region is wounded. It holds more tension, more strain. That strain would subtly skew polarization alignments. If the asymmetries are non-Gaussian, non-random, and spatially correlated to the cold spot, that's a huge point in favor of MCM. Third, we anticipate gravitational lensing anomalies. In the standard model, gravitational lensing is a result of matter density curves along the line of sight. But in MCM, there's another factor: memory tension itself. That deep fold left by the rupture, while not visible as matter, might distort light paths. It would act like an invisible lens, subtly warping the photons traveling through it. So if lensing maps show a strange distortion around the cold spot that doesn't match visible matter, MCM predicted that. And fourth, we predict a non-thermal spectral profile. Photons from the inflation era should have a predictable energy distribution, essentially thermal blackbody radiation. But if the cold spot is older in memory, if it's a pre-inflationary scar, then the energy distribution might be off. Slight shifts in photon temperature, polarization entropy, or residual anisotropies might mark this area as something else entirely, a cosmic wound, not just a cooler region. These are testable. They might not be easy, but they are within reach. And unlike theories that explain away anomalies, the MCM embraces them as clues, evidence of a deeper structure. Let's move into the philosophical implications of what the Millar Cosmological Model reveals about the cold spot, time, and memory. Philosophical implications. To many cosmologists, the cold spot is a nuisance, a data point that doesn't quite fit the standard model. But in the Millar Cosmological Model, it's not a nuisance, it's a relic. It's the first scar in the fabric of the universe, a place where time itself began ticking. And this changes everything about how we think about creation, directionality, and meaning in the cosmos. Standard cosmology relies on symmetry, the idea that the universe looks the same in every direction. But MCM introduces asymmetry as a meaningful structure. The shatter wasn't smooth. It had an arrow, it tore space in a single direction, and from that rupture flowed the universe. And that idea ties back to something deeply human. We don't live in a symmetric world. Our lives are full of scars, of directional moments that shape us. The cold spot, then, isn't just scientific, it's spiritual. It's the cosmic memory of the first breath of everything. In theological terms, it's the moment when stillness gave way to creation, when let there be light left its first physical mark. In that light, the cold spot is a kind of Genesis coordinate, an artifact not just of physics, but of purpose. So the MCM doesn't just offer a new scientific explanation. It invites a conversation between science and spirituality. It dares to ask not just how the universe began, but why it left behind a memory of that beginning. And if that memory is visible, maybe we were meant to find it. Section 6, Conclusion. reframing the cold spot. So, what do we have? A strange cold blemish in the sky, long dismissed as statistical noise or line of sight structure. But under the Millar Cosmological Model, that blemish becomes something else entirely. A signature, a directional scar on the memory fabric of the universe, created by the rupture of the Chrissy Core, a zero-point singularity from which all space, time, and mass emerged. In this model, time isn't a flowing dimension. It's a record written by discrete blips, the appearance and disappearance of quantum structures known as arnis. Each event leaves a mark. Each disappearance creates space. Each moment is stored. And the cold spot is the deepest, oldest imprint of all. Not a random dip, not a void, but a cosmic testimony, the first mark on the ledger of reality. And here's where it becomes personal. Our galaxy, our solar system, our very point of observation, we are moving. We are flying through the universe at over 600 kilometers per second, heading straight toward the Great Attractor, a region of enormous gravitational pull. In standard physics, this is unexplained. But in MCM, this motion is expected. We are on a trajectory, launched during the Shatter, carried outward in the direction of expansion, away from the cold spot. That's why it sits where it does in the sky. That's why we can see it. And that's why we're moving towards something massive, not a random attractor, but the forward arc of the original rupture. This isn't just astronomy, it's positioning. After 14 billion years, we are in exactly the right place to look back at the cold spot and realize what it truly is. And that, to me, is not a coincidence. It's a call to remember where we came from. Inc. Thank you so much for being part of this journey. If the cold spot really is the scar of the universe's birth, then we're not just observers of the cosmos. We are its witnesses. If this made you think differently about the universe, please like, comment, share, and subscribe. And as always, we'll see you on the other side of the fabric.